All right. Time for lesson 3 of unit 1 of pre-calculus. I'm excited. Are you excited? Well, let's dive on in. This particular lesson, it's worth noting, is maybe a little bit trickier. For it might be a little bit trickier for some of you because in this lesson we really are starting to prepare for calculus specifically, and this lesson has got a concept in it that is maybe a little bit different. It's not just do this thing and this, if problem look like this, do this. It's understanding something. We'll get into it. You'll see what I'm talking about, but strap your thinking brain on for this one because you're going to need it. All right. So the first thing we're going to talk about is pretty straightforward, and that is a function being continuous. And it's worth noting that when we're talking about continuity, we're talking about at any given point. This a completely continuous function is one that continues as is a smooth curve throughout the whole thing. A straight line would also be continuous, right? It would be continuous throughout its length. If a function has a hole or something else, then it is discontinuous. There are, in fact, 3 types of discontinuity. Let's look at those. So the 3 different types of discontinuity are infinite, jump, and hole, right? So infinite discontinuity is where the function has a break in it, like maybe this reciprocal function, right? It has a break where it doesn't continue here. And we call it infinite discontinuity because it keeps on going to infinity, right? So it breaks off at infinity. You could also have something that looked like this, right? That would also be infinite discontinuity. So they don't have to be going in opposite direction. I'm doing a terrible job of quickly sketching that little example in there, but you see what I mean. So this would also be discontinuous at this point here, but it would be infinite discontinuity because it's stretching to infinity. Basically, if you have an asymptote at a space, then it's going to have infinite discontinuity, probably, unless it's a slant asymptote, and even then you probably still have a discontinuity there, a infinite discontinuity there. We'll get more and more detail, more examples as we press on. So a jump discontinuity is something like a piecewise function, is something like this, something that's defined piecewise where it jumps from one place to another, right? That's what that is. And the third type is a hole, like it's straight, it's completely straight, but it's got one number that doesn't exist for it. I threw in an example later of something specific, a specific situation where that would be the type of discontinuity, because it might be kind of hard for you to remember from Algebra 2. We've actually seen functions with a hole discontinuity before in Algebra 2, presumably, if you had a decent Algebra 2 class. But you have slept since then, right? And so you may not remember it. So I added that in, and we'll look at that in a minute. Now, in order to understand how to find a discontinuity, we have to understand kind of Calculus 101 topic. This is the kind of the beginning of calculus, and that is limits. So what is a limit? This is the concept that is a little bit confusing. So you can do it. We can do this. So a function exists in a certain place. Like if I have a function is defined at a specific place, and let me write some concrete letters to what I'm saying. So if I have the function g of x and it equals 3x, right? Let's do a simple little linear function kind of pseudo example here. It is defined at x equals 2 because g of 2 is 6 because we substitute that 2 in there, right? And 3 times 2 is 6, right? So it's defined there. It exists there, right? So the limit is not a static place like that, right? A limit is where the picture is approaching. We use the word approaching. We can see it right here and right here. Oh, I never fixed that. Let me pause. I'll be right back. I'm back. Okay. So A limit is where as the graph travels. Oh my gosh, I didn't fit. Oh my gosh, let me pause. Be right. I made the prep for this video in multiple sittings, and so obviously I forgot to go back and finish filling in this slide. Anyway, as we're tracking in a particular direction, where is this graph headed towards, right? So this kind of linear parent function right here, and wait, back up. Let's explain the green first. You could approach something from two different directions. So if I am trying to get to this point right here, if I'm trying to get to that point on this linear function, I can approach that from the left, or I can approach it from the right if I am traveling. So this is what I'm talking about, where a limit is not a static thing. It is as we're moving closer and closer to the thing, what are we approaching, right? And so where are we headed? What y value are we headed to? So like, let's say that this number was a x3, right? If this was the linear parent function, we are approaching 3. That's where we are approaching. Now, this also gets there, and that statement's going to be important for the next slide. It is not only approaching that, but it also gets to that point, right? So if we have something like this, where it's not all, where it has, that is discontinuous, so something like this green one or something like this red one, this little red piecewise function or this little green reciprocal function, if it's discontinuous, then the limit might be different than its definition, right? It's in fact, that's, well, let's not get ahead of myself. So in this instance, in this red instance, as I am approaching and getting closer and closer and closer to to this one space, if I'm approaching from the left, then I am approaching this number here. I'm approaching -3 if I'm coming from the left. It doesn't actually get there, because if I put in -3, it actually is this one. So it jumps to the other thing, jump discontinuity. But if I'm approaching this, if I'm approaching -1 from the right, then it's approaching this number, which would be 2 in this instance, I think. I don't know. I'm not going to worry about thinking through that. It might be 1. No, it'd be 1. If I put a 1 in here, then we get a 1 out. Yeah, we're not going to relearn piecewise functions at the moment. We may later. Possibly spoilers for the future. We won't stress about that. But as we're approaching from the right, we're approaching this number, and we get there, right? And that's going to be important. That idea in a slide. We hanging in there. This is one of those things where I wish I could see your face and we could talk it all out. Let's talk about the green one. As I'm approaching x equals 0, so as I'm approaching here from the left, the graph is getting closer and closer and keeping on going, and it's getting closer and closer to infinity, negative infinity. So if I come from the left, then it is approaching negative infinity. It's going down and down and down. It's excuse me. It's never going to get to 0, and it's never going to get to negative infinity either. If I'm approaching it from the right, then it is getting closer and closer to positive infinity. So the limit is where the graph is approaching at, and when we're headed towards whatever x value. As x gets closer and closer to some number, as x is moving closer and closer to some number, what is it trying to get to? Now, sometimes it gets there, like in this one. Sometimes it does get there, but sometimes it doesn't get there, and that's where you can have a limit even if something isn't defined, right? If we put a 0 in here, 1 over 0 is not defined. It does not exist, right? D and E, yeah, it doesn't exist there, but it does have a limit. Its limit is plus or minus infinity, depending on which direction we're going. So you can have a limit somewhere, even if a function doesn't exist there. So we're putting limits with continuity together, right, to make some tests for continuity. So a function is continuous at a specific value of x if it satisfies these conditions. So in order for a function to be continuous at a specific point, at a specific x value, all these has to be true. First of all, f of x has to be defined at c. So you have to be able to put the number, whatever it is, in for x and get a real answer out of it. Not an imaginary number, not a does not exist, but a real number, right? You have to be able to get that out of there, and that's if it does that, then the first condition is checked. We're going to do some examples of this in a minute, which will help, I think. So the next condition is as x approaches the same value from either side, f of x approaches the same value from either side of c. So that's like in this guy, this doesn't meet that criteria. It actually doesn't meet either of the first two criteria, but this doesn't meet that criteria because as we're approaching from the right, it's going to negative infinity, but as we're going from the left, it's going to positive infinity. This one doesn't meet that criteria either, but it does meet the first one, right? Because if I put a -1 in here, then I get a 1 out because that exists right there at that solid dot space, right? But it doesn't meet the second criteria because as we're approaching from this direction, it's approaching down here. And as I'm approaching from the right, it's approaching up here. So if it's approaching two different spaces, depending on where it's connected, then it's discontinuous there, right? The last condition is it has to be the same. So the limit of f of x as x approaches c has to be the exact same number as f of c. So it's like in this example here, it has to not only be approaching it from both directions, but it has to get there. And I made a note on this page. From this page here, if we have the number and a little plus, then we're saying we're approaching it from the right. If we have a little, also didn't fix that. Pause again. If it has a little minus there, then we're approaching from the left, right? If it has neither one of those, which is like this one, but I made a special note of it on this, that if it doesn't have a plus or minus, then that means from both directions. So this is saying as we approach the number from both directions, then it's the same number. So like I was saying, like on this one, what I kept saying is as it approaches, it's approaching the number, and then it actually gets there. It actually exists there. It actually is the same number. It's approaching and hitting the target. So it approaches and hits the target and the other two conditions, then it is continuous at that particular point. Let's put some meat on it with some examples, okay? So here's our first example. Is f of x, I don't know what that line is, but, it's fine. Is f of x equals 2x minus... I'm struggling. It's late. I'm trying to get this video out and done. Is f of x equals 2x squared minus 3x minus 1 continuous at x equals 2? And we're going to justify our answers using that continuity test. So what we're going to do with this is, since we're in pre-cal, what we're going to do is, we could go back to algebra 2 and we could graph this by hand and we could figure out its roots and we could figure out the vertex and we could figure out all those things and we could do all that stuff. And actually, this you can just tell me with your brain because in algebra 2 and maybe even algebra 1, you would have figured out that this is a parabola, right? And this is a parabola, and we know that a parabola is always continuous. It has no holes, no gaps. It just goes on and goes up. This one's opening up because A is positive, right? So this is a parabola opening up. You hopefully recognize that already. So you know it's going to be, yes, it is continuous there. You know that. But we're going to justify it using the continuity test, and we're going to graph it on a graphing calculator, and I'm going to show you some things. So it's worth noting that I'm probably not going to be using the graphing calculator that you have. If you're in my class, you have to have a graphing calculator. If you're in my pre-cal class, at least, or if you're in public school or whatever, you may have something different. I'm using this graphing calculator. This is what I use for my videos and on my computer. Unless I'm making pictures, and then I probably use Desmos. But I'm using this guy because its emulator is free. Now, everything I'm about to show you on this calculator will be able to be done with your graphing calculator. You may have to look up how to do it, but it can be done on your calculator. And so this is what we're going to do. I'm going to show you some puzzle pieces and all of those things. If you're in public school and you have a graphing calculator, you can look it up on Google, or you could even just ask your teacher. Or they may have told you already. So let's stick it in the deal. So we've got 2x squared minus 3x minus 1. And then we're going to graph the thing. So we were right. It was a parabola. So that's great. So at x equals 2, so it may be kind of hard to tell where it is from the picture, right? It's not quite at 0. It's close, right? But it's not quite there. It's up a little. So what your calculator also has somewhere is a way to get to a table of this function. So something like this. You also can do on your graphing calculator, you can scroll through these numbers, right? And find different numbers. You can probably use your up and down keys or whatever else. You probably almost certainly have a way to go to a specific value on here. So we can go on this table to to 2. And then we can look around here, and it is approaching 1. It is 1. It is getting closer and closer to 1. These numbers. Now, it may be kind of hard. Right now, I have this set to stepping every 10th. You can also, in your calculator, be able to change the step value. That's going to be somewhere in your calculator. So you may want to change that step to something smaller so you can see where it's actually approaching. So you can change, like I might change it to 0.01, so 1/100th, which is this definitely makes us want to be able to use that goes straight to the value. But you can see that as we get closer and closer to 2, these numbers are getting closer and closer or approaching 1. So it exists, first criteria. So f of 2 equals 2 is our first bit, right? And then from the table and the second bit of the table, we could write our table so we show that our teacher that we've done something. We can make a little table of values, and we could put in a handful of things. So we could put in 1.95, 1.96, 1.99 maybe, 2, and then on the other side we could do 2.01 and 2.02 and 2.03, right? I can do better than that. I can use my ruler. And then you can you could go in and put in those values to show that it's getting closer and closer to that number. So it is approaching that, and it is that. For the sake of brevity, I may not fill in this whole table on this video so that you don't have to sit and watch me just copy numbers from a calculator for an hour and a half. All right? That sound like a good idea? Sounds like a good idea to me. If it didn't sound like a good idea and it was less helpful than I figured, let me know in the comments. But you can go ahead and fill in the numbers. You can fill in a few things. 0.999502, 0.9502. Is this the vertex? This is not the vertex. They're not going to be the same on both sides. 1.005. 05 and 0.90, 0.85. You get the idea. So they're getting closer and closer to 2. So the limit, it's approaching, not closer to 2, it's getting closer and closer to 1. It's approaching 1, and it gets there. So it meets all the criteria. So yes, it is continuous, right? Makes sense. Let's do another one. Another 2. All right. So you probably are going to know what kind of discontinuity these are going to have because of what I've reminded you of in this video and from your work presumably in Algebra 2, right? So this is going to be a piecewise function, and you can probably tell what's going to happen. It's going to jump at -3, right? But let's stick it in your calculator. Now this is probably something that you're going to have to look up on your graphing how to do on your graphing calculator. This I have to look it up almost every time on almost every calculator I use. Which this one you'd think you would remember because it's actually super easy. It's just in here and then it gives you a definition of it. But wherever it went, there it is. But your calculator is going to be different. Some of them use a comma button. Some of them use different symbols, different whatevers. There's all kinds of different ways that your calculator may let you put in a piecewise function, but it almost certainly lets you put in a piecewise function. So let's put this one in here. 3x minus 2. And then that's if x is greater than negative 3. Oops, not 6. We want symbol greater than. It's worth noting, if you're watching this video, you probably know this already, but almost certainly on your graphing calculator, there is a minus button, a subtraction button, and a negative button somewhere, and they're almost certainly not the same button. And so don't make that mistake. Again, you probably knew that one if you're watching this video. But if you didn't, you're using a calculator that you barely know how to use or don't know how to use, then it has those buttons. Right? And negative 3. Okay. So let's graph the thing. It is in fact a piecewise. I can't do what I'm trying to do on there. It's got a touch screen on it, but my screen isn't a touch screen, so I'll just scroll and show you. Look at there. It's discontinuous. So it is discontinuous. Discontinuous at negative 3. What kind of discontinuity is it? It is jump discontinuity. And if we go into our table and head to negative 3, no, not that one, negative 3, why is that a syntax error? Negative 3, okay, thank you. Excuse me. So it does exist. It does exist. But notice on our table, we're going to draw our table if we're coming from the negative direction. So if we are approaching from the left, if we're scooting on over from the left, it's approaching 5. But if we're scooting from the right, it is not approaching 5. It looks to me like it's approaching negative 11. Right, and we could put in some more we could add some more steps in here, and we could further prove that it was approaching negative 11. We could justify it with algebra by sticking a number over here, and figuring it out. If we put a negative 3 in here, then we end up. It's late, and my brain got confused for a second, but I'm back and I'm not confused. If we're approaching from the right, we're talking about this one, right? When x is greater than, so we're talking about this one. So we plug a negative 3 into here, and and you can prove it yourself on your own time that you'll get a negative 11 when we plug it in up here. So it's approaching from the right a negative 11. So it is, excuse me. So since it is approaching two different numbers, it does exist there, but it's approaching two different numbers, it's discontinuous. And specifically jump discontinuity, right? Let's do this one. So go back to our graph here, clear it out, and then we're going to put in the new one. So we've got this radical function, not radical. We have this rational function. That's what I'm trying to say. Oops. That's not what I wanted. I wanted x plus 3 x, thank you, plus 3. I would recommend, if you're not, it's a little late for saying these words, but we've still got more stuff to see. So I would recommend, if you aren't doing this, to follow along on your calculator on what I'm doing. See if you can make sure you're able to do what I'm doing. I think that would be a very wise idea. So this is an interesting graph, right? We want to zoom in a little bit, right? So it's got this little bumpity bump looking thing. All that stuff is going on, and it's kind of bumping around, and something I don't know what's happening here. What is happening here? We'd have to get some more details and all the things to figure out what's happening here. And luckily, we can use our tool to do that. So we're interested in continuity at +3 and -3. So is it continuous at +3 or at -3? So let's head there. So at -3.0, sure, why not? -3.0. It does exist. So the first criteria, it works. It gets there for at 3. It gets there. Now, is it approaching the same? Is it approaching the same value? So this one, now notice, it's important to note that excuse me, that these numbers here are not -5.5. You want to pay attention when you're looking at your table. These values are actually -5.5 times 10 to the -4. So itty bitty negative number. So it's getting tiny negative number. It's approaching tiny negative number. So if these are the axes, it's getting littler and littler, closer and closer from the bottom, because it's negative numbers. So it's getting closer and closer actually to 0. So it's getting closer and closer to 0 from this side. So what about this side? What about this side? From the right-hand side. So from the positive side, it's now their positive side. So it's getting closer and closer to 0. So it's getting closer and closer to 0. So does that meet our criteria? Let's go back and remind ourselves what the criteria were. So what were the, oops, wrong one. How about this one? So what were they? It's defined, approaches the same value from either side. So it's approaching 0 from both sides. That's good. So does the limit, now, so this last one, is the limit the same as what it's defined as? Let's go back. Let me pull back. Let me pull back where we are and pull back our thing. So the limit, it's approaching 0. Where does it get to? 0. So it's the same as what it is. So this is continuous at +3. So it is continuous. All right. Continuous at x equals 3. What about x equals -3? Let's go back and look. Oh, no, that is -3. Oops, my bad. Sorry. I meant to put in 3, but the negative was already in there, and it stayed in there. And so, yeah, at -3. What about +3? Let's take a look. Let's go to that place on our table. At +3, it does exist. Does not exist. There's some sort of error looking thing. It does exist there. It exists at 0.333 repeating, so a third, right? So it's approaching. It's getting closer and closer. These numbers are getting closer and closer and closer to 0.33 from the left. From the right, these numbers, as they get closer and closer, they're getting closer and closer and closer to 0.33. So it's approaching the same number from both sides. Is the limit the same thing? Well, it's approaching 0.33, and it is 0.33. So it's also continuous at x equals 3. Great. Now, I threw in this one as a bonus. We don't necessarily have to write all the things, but I wanted to talk through this one. This is, I said that this one was coming earlier, so let me put this over here. So let's add this one into our graph. clear this out of here. And we're going to put in x minus 2, x minus 2, minus 2. Come on, thing. X minus 2 times x plus 3. And then all that over x minus 2. Minus 2. I'm in trouble with that minus symbol for some reason. And that's what we want. So when we graph this, it's a straight line. It's a straight line. So yeah, it is. It's a straight line, and the straight line is going to look like f of x equals x plus 3. The straight line is going to look like that, right? Because those would cancel and leave you with just that. So this is going to look like a straight line. It's going to look like the straight line f of x equals x plus 3. So you might jump to say, oh, this is continuous. This is continuous at x equals 2. So is it continuous at x equals 2? Well, you may be thinking, well, if I put a 2 in here, it's going to break. It's because I can't divide by 0. It's going to be divide by 0 error. Let's look at what happens on our table at x equals 2. Let's put a 2 in here. None, whatever that means. I have to look up what that code means. But what it means in English, in plain English, is it doesn't exist there. So this one is also discontinuous, and it's a whole discontinuity, right? So little bonus. We're almost through. This is not a short video, but shorter than 50 minutes. But here we go. One more thing. One more application of limits. So end behavior. This is kind of the algebra way of looking at end behavior. We'll look on the next slide at a couple of examples, and then we'll be out. So end behavior is as x approaches negative infinity, so there can be left end behavior. So what does the graph do as it keeps on going forever and forever and forever to the left? What is it approaching? Is it a parabola that's going up and it's approaching positive infinity? It's getting closer and closer to positive infinity. Is it a exponential type function where it's getting closer and closer to 0? If it's a exponential growth function, all of those things. And in behavior to the right is the same idea. It's what is the graph doing as it approaches positive infinity, right? So let's look at a couple of examples, put some meat on that, and then we're going to be good. Now, problems like this in your homework or whatever, they may actually provide the graph, but as we're practicing putting in graphs, I thought I would do that for you, but I'm going to go ahead and to save us time, I'm going to pause and you can go put it in and I'll put it in and we'll be right back. All right, so when we punch that first one in, it looks like something like this. I was going to mention another feature that your calculator may have and may not have. A lot of calculators have this feature, but this feature might be lacking on your calculator depending on what it is. But on the zoom feature, a lot of calculators have some sort of auto scaling or auto zoom to where it kind of tries to figure out how to zoom it in a way that fits the whole thing. So that's mine looks like this because I use auto scale, which is actually not the greatest. I think I'm actually going to hit zoom out just a little because then we actually can see the end behavior. If we had that other zoom, we may not. You may need to zoom out whatever you do so you can figure out the end behavior. So the end behavior as x approaches negative infinity. So as we're going to the left, what is the graph doing? Y is approaching negative infinity. It is going down and down and down. As the limit as x approaches positive infinity. So as we go farther to the right, it's going down and down and down, right? So it's approaching negative infinity. So what I'm going to do on my answer bit is I'm going to first kind of draw a really rough sketch, and when you're doing this, you can do the same. At least in my class, you can do the same thing. Just kind of to give yourself and myself a reference for that you did it. Now, actually, in my class, you probably don't even need to do this, and if your textbooks is the same way, then the textbook gives you the picture in the homework. So, whatever. But now, to write our answer, the limit as x approaches positive infinity, so as it goes to the right of f of x is negative infinity. So that's what it's approaching, right? It's getting closer and closer to negative infinity, going down. And then the limit as x approaches negative infinity of f of x is also negative infinity on this particular graph. Now, there's this little other bit in the instructions. It says support your conjecture numerically. Okay, so what we're going to do is we're going to add a table. That's what we're talking about, where we support it numerically, right? So we're going to add x and an f of x. As far as my class is concerned, you can certainly do a horizontal table like this or a vertical one. And we're going to get, I'm going to put 5 values on here. 1, 2, 3, 4, 5. All right. So on our table. Now, what we're going to do when we set our thing, we're going to want to change that scale, because we don't, these little tiny little numbers in there are close. We need numbers that are really big and really little. And so what we want to do is we want to change the step value. So I do that this way. Your mileage will certainly will certainly change. So I want to change my step value to 500, right? And we go back to it. And I'm going to center it at 0. So I want to get the middle. So I'm going to put that 0 point in the middle of what we're doing. So I'm going to put 0. So in the middle, it is at negative 80. 80. And then I'm going to put in 1,000 and then like 2,000. So as we go to negative 1,000, you could even go bigger and go to like 10,000 if you wanted to. Negative 1,000, negative 2,000, positive 1,000, and negative 1,000, negative 2,000. It's late. We're almost done. I should have just left that. Penance for my brain starting to be tired. Left the 3,000. All right. So at negative 1,000, it is at 1.0 times 10 to the 12th. Negative 1.0 times 10 to the 12th. And at 2,000, it's negative 1.6 times 10 to the negative. No, not negative. No, that would mess it up. That we would disprove our theory at that point. Times 10 to the 13th. So a way even smaller number, even more negative number, right? And then at positive 1,000, it's at negative 992. You notice I'm like not being very particular about our rounding. My rounding here, or my like the place that I'm rounding to, or the how many significant figures, because it's not really the point. The point is that they're getting smaller and smaller and smaller and smaller and smaller. That's what we're trying to show here. And so if we were trying to do something formal, we might keep it all consistent. But for what we're doing here, we're just getting the rough idea that, yeah, this is getting smaller and smaller and smaller. So at 2,000, it is at 2,000, it is at negative 1.6 times 10 to the 13th. So a huge jump there between here and here. Negative 1.6 times 10 to the 13th. So it's getting smaller and smaller and smaller. We saw it on the picture. We proved it well, we supported it. Technically, it could, this one won't, but there could be a function that dipped and dipped and dipped for a really, really long time, and then all of a sudden, like, went up because of some trigger or something. There could certainly be a real life situation where that was a thing, but we're supporting our conjecture numerically is what we're doing. Okay, let's look at this one. I'm gonna do this. I'm gonna do the pause and come back again. You punch it in your. When we graph it, it looks like that. And I did the same zoom trick. I did auto scale and then zoomed out a few times just to think that we're just to kind of make sure we're getting a good feel for the graph and what it looks like. This is a cool looking graph. It's got all kinds of fun things happening here, and it looks like to me from just looking at the picture that as x approaches negative infinity, so as it continues going to the left, it looks like we're approaching zero. It looks like we're going to get closer and closer to zero. Never quite touch it there. Looks like, and we could prove algebraically whether it did or didn't have a horizontal asymptote there. Excuse me. All of those things are true. It looks like as x approaches positive infinity, it's also approaching zero. So the limit is almost certainly the limit as where the negative left end behavior is almost certainly zero. The right end behavior is almost certainly zero. We'll go ahead and pull up. Actually, I'm going to add, just for consistency, I'm going to add, and it's kind of a cool picture anyway. So we've got this little shape with the bigger shape, and then it looks like that. But bam, 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 with a zero. No, I just wrote it. Something like that. It looks like that. A weird shrug face. I don't know. Right? There it is. Great. Beautiful. Grandness and gloriousness. Let's make a table to support our conjecture that the limit of f of x as x approaches positive infinity is 0, and the limit of f of x as x approaches negative infinity is also 0. I'm going to support that with a table. I need a much smaller pen than what I'm using. Probably fine for the x. I'm going to make my boxes a little bit bigger. I didn't do it good enough the first time. F of x. We'll use the same values. I think those are going to be fine. Let's double check on our table, see if that does what we want it to do. Negative 2,000 is getting smaller and smaller, right? It's getting closer and closer, and as we scroll up, it's getting closer and closer to 0. Oh, that e to the negative number means that it's a little number. So these numbers are getting littler and littler, littler, littler and littler and littler negative numbers. And on the other side, we're getting littler and littler and littler positive numbers. So definitely approaching 0. It's not quite ever going to get there. Error on the end behavior part, it does cross 0 in the middle. We see that there. But it's getting closer and closer and closer to 0 on both sides. Let's add that to a table. Here we go. Make myself a little bit more room so it can look less derpified. This one can be small. We already know that. So make my pen even a little smaller. We're going to put in the same numbers because it's supporting it well enough. Negative 2,000, negative 1,000, 0. We remember that one was 0, or I do, because that's an easy number. Sticks in your brain. And 2,000. And you wouldn't have, but by the way, I should note, to support your conjecture, like I said earlier, you don't have to choose these specific values. Just like a couple of rather large numbers and a couple of rather large negative numbers, right? That's what we're wanting to see. So 1,000, it's at negative 10 times 10 to the negative 4. Negative 10. I know this isn't really quite correct scientific notation, but again, we're really just trying to get the point across, as it would be If we want to do correct scientific notation, since I moved the decimal, we'd have to do -1 times 10 to the -5. I know that, but we're getting the point across here. So 2,000 is -5, -5.0. We'll go ahead and we'll make up for the ugly one by doing this one correctly. -5.0 times 10 to the -4. Little bitty number. And on the other side, we've got 1,000 is 2.0 times 10 to the -3. Little bitty tiny number. And then we've got 5.0 times 10 to the -4. So it does appear supportedly to be approaching 0. And that's it, folks. It is under 50 minutes. I wasn't wrong earlier, but barely. So that's pre-cal for you, especially in some of these earlier things. There's just a lot in it, and it's fun. It's great. I hope y'all are having fun. I'm having fun. Don't forget to like, comment, and subscribe. And if you're one of my students, do your homework. We'll see y'all later. Bye-bye.